Bonjour et bienvenue. That's probably the limit of my French, I'm afraid. Welcome, everybody, to the conference. Merci. I'd like to echo the things that we started the conference with. I've become really interested in the ideas that are pervasive, foundational to our discipline. The things that, it doesn't matter what the technology that you're working in or what the software that you're building, are applicable. And I think I've found some. Well, I don't think I found them. I think they've been around for a while. But I've pulled some together to try and make a more cohesive story. And that's really what I want to talk about today. This is the idea of modern software engineering. So let's start that by thinking about why my pointer's not working. Okay. Let's try doing like that. So what is engineering? And I think we can start to think about lessons that we can learn from that. I think in other disciplines, what we think of is that engineering is really just the stuff that works. In other disciplines, if it doesn't work, we change it until it does, and then that's what engineering is. And I don't think we tend to have thought of that about it like that in software very much. But software is a really difficult thing to do. And I'm going to see if I can make my pointer work so I can walk about more freely. And see if that works. Yes, it does. Good. So what is the stuff that works for us? I've been talking about software engineering now for a few years, and one of the strange things about that is that I've ended up having quite a lot of conversations about bridges. What usually happens is that somebody says, yes, Dave, but it's not bridge building, is it? And of course it's not bridge building. Of course it's not. But then I think that when we say that, what we really mean is something else. I think that what we really mean is not really bridge building either. And bridge building is not the same as house building or chemical engineering or shipbuilding or rocket building. They're all different. Engineering is different in different disciplines. So one of the first things that we can say is that if we could identify genuine engineering principles for software, they'd be different to other forms of engineering. And so I think there's something interesting there. Today I'm going to pull some examples from 3 different other fields of engineering just to kind of highlight what I think are some of the important principles that are common. Oh, and I might talk about Lego a little bit as well. But what does this really mean for us? Why is this relevant and what can we do about it? A good starting point is what is engineering. And the definition that I used in my book, which I kind of like, I would do because I wrote it, I suppose, but engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. I think certainly when we think about modern engineering, then it's really kind of like the practical arm of science. It's ancient engineering was something different, but modern engineering is really about applying scientifically rational styles of thinking to solving real-world problems. And I think that's a pretty good definition that we can use and we can get benefit from. To put it more simply, engineering is the way that we solve the hard problems. Whatever they are, that's how we do it. Whether it's building a COVID vaccine, that's a kind of engineering. Whether it's building spaceships to be reusable, as SpaceX are currently doing, or whether it's building large hadron colliders, it's engineering that really comes to the fore when we're trying to do the hard things. It's actually the foundation on which our society is built. We've existed as a distinct species. Scientists argue about this, but it's somewhere between 200,000 and 300,000 years. The people from 200,000 or 300,000 years ago were us. They were Homo sapiens with the same number of neurons as us. But if you look at progress, that hasn't been some kind of straight line of advancement because we're smart, right? It's more like a flat line for 200 or 300,000 years, and then something happened just a few hundred years ago, largely. Here's a graph estimating technological progress. And you can see this doesn't go all the way back to the start of human beings, but it goes back quite a long way. And you can see that something happened just a few hundred years ago. And the thing that happened was science. Science was the thing that liberated our ability to, in our context of this conversation, start doing engineering, really. Here's another graph. This is from Buckminster Fuller, who was an IBM fellow and a researcher and a polymath genius. But in 1982, he thought it would be interesting to try and estimate the rate at which all human knowledge doubles. And he came up with this model. In 1900, he estimated that human knowledge, all human knowledge, was doubling at the rate of once every century. By 1945, it was doubling every 25 years. By 1982, when Buckminster Fuller did the work, it was doubling every 12 to 13 months. A recent revision of his work, I'm not quite sure I buy this, but nevertheless, a recent revision of his work said that knowledge, all human knowledge will be doubling, this was before 2020 obviously, would be doubling at the rate of every 12 to 13 hours. And that's largely because it's not always us now that's doubling the knowledge. It's other things, other systems, computer systems that we built. In terms of where this stands historically and in terms of progress, science is over there somewhere and computers and software is here. So we're living through something interesting. We're living through interesting times and things are changing. So what is engineering really for? If it's this practical application of kind of scientific style reasoning to solving problems, what's it really for? And I think we get that wrong. Us software people, often get it wrong and we think about the wrong things. I often have people that say to me, yes, Dave, but we can't precisely cookie cutter predict what's going to come. No, engineering never does that. Engineering never tells you a single solution to any problem, ever. That's not how it works. Engineering does this. Engineering doesn't tell us what the answer is. Engineering rules out the stupid ideas. It tells you what the answer isn't. It tells you don't do that because your aeroplane or your spaceship will blow up. And sometimes, though, that learning comes over decades or even centuries. But that's how it really works. So engineering, as I said at the start, if it's not the best way of doing things, we change it until it is. And we keep refining it over time until it is. I think that the mistake that we make is this, and I think this is fundamentally the mistake that we've made in software for many, many decades, and that is confusing engineering, but also what we do with manufacturing. And we don't have a manufacturing problem. Manufacturing is never our problem. And so this is not our problem. This is not what we need to fix. This is not what we need to solve. Our problem is extremely different. And we're going to start off with something like this, some code of some kind. And we're going to think hard about this code. And then we're going to do this. We're going to generate a stream of bytes. And the unique thing about a stream of bytes, really, is that for essentially zero cost, or close enough to be, negligible cost, close enough to be zero, we can perfectly clone that stream of bytes. So we never, ever, ever have a production problem. We never, ever, ever have a manufacturing problem because we just clone the stream of bytes. The hard part is coming up with the stream of bytes in the first place. That's our job. That's our profession. That's our complicated problem to solve. And that's a very different thing, because if we can just press a button and clone the stream of bytes as many times as we like, then why on earth would we ever be trying to get a repetitive, predictable process? Because it's never going to be repetitive and predictable, because if it was, the economics say we should just copy the bytes that we had before. If we were producing exactly the same thing that we had before, we'll just copy the bytes that we had before. We'd be stupid to do anything else. Our problem is always, always, always creating something new, and therefore we need a different set of skills and techniques to manage that. So I would argue that engineering is always about exploration and discovery. And I would argue that software development, too, is always about exploration and discovery. That's our job. That's what we do. So what's the stuff that works if we need to think about that? Well, I think it divides into two categories, and I want to talk about both of those today. The first one is optimizing for learning. If we are always in the realm of exploration and discovery, then what we must do as software professionals is become excellent at learning. So we optimize for learning. We do what we can to learn faster and better, more effectively. And then we build systems that are beyond the capacity of any human mind, really, to hold them in their entirety and all the consequences of them. So we must also become experts at managing the complexity. So we can work on one part of the system without breaking another. We can understand one piece of the problem without having to understand the whole thing. And so we need to do that as well. And I think that's it. I think that's fundamentally what we all should be doing. So let's talk about these. I have 5 different properties that I think help us to do each of these things. So the first one is optimize for learning. And all of my 10 properties, you'll be familiar with them. These are not new ideas. But I'm proposing something slightly different. I'm not just saying, aren't these things nice? I'm saying use these things as tools. Always optimize to do more of these things as your first step. When you don't know what you're doing, always work iteratively, be experimental, be feedback-driven, be incremental and empirical, always, because that's what engineering is. And that's going to rule out the stupid ideas. Let's look at each of those in turn. So I said I wanted to pull some examples. This is the Wright Flyer. This is the first first aircraft that was controllable, powered, and capable of flying a human being. I'm being precise about all those definitions because there were other forms of aircraft that predated them that did solve parts of this problem. That's another way in which engineering works. But this was the first one in 1903. December the 17th, my young eldest son's birthday. He's born on the day of the aeroplane. So the Wright brothers came up with this machine. And looking at this now, with the benefit of over 100 years of progress, this looks very crude. It looks like the product of craft. It wasn't. The Wright brothers were engineers. They were good engineers. They did research. They did the calculations. They advanced the maths and the science of the lift-drag equation, for example. They were the first people to build a wind tunnel to measure the effectiveness of aerofoils, to be able to understand how to build a machine like this. They built their own engine, and they designed the lightest ever petrol engine to power the aeroplane. So they were doing some difficult things with crude technologies. But at this point in the history of the aeroplane, these things were death traps. And for 20 or 30 years afterwards, nearly every aviation pioneer during this period, or at least a high proportion of them, was killed by the machine that they were pioneering in. These were dangerous things. And then what happened is what happens in engineering. People learnt some things, often by other people dying, but they learnt some things from these, and over time, designs were refined, standards were applied, approaches were improved, until we got to something like this. This is the DC-3. This is an aeroplane that was designed just prior to the Second World War, and was one of the first really practical aeroplanes for taking passengers long distances. There were other aeroplanes that did that before, but this was safer and faster and more comfortable, all of those kinds of things. And then progress continues until we get to a modern commercial airliner. In 2017, commercial airliners flew the equivalent of 2/3 of the population of the planet. And in 2017, no one was killed by an aeroplane accident. That was the first time that had happened. But that's remarkable progress. That's unbelievable. The statistics are ludicrous. We are in more danger in this room than if we were sat in an aeroplane flying somewhere. That's what the statistics say. And that's the kind of advancement that we can have by adopting engineering and not trusting just on let's be geniuses and think of everything, at the beginning. We try stuff out, we find out what works, and we change things. This is based on the idea of iteration and exploring. Iteration is a remarkably powerful idea. It seems more ad hoc. It kind of feels as though this is not quite as rigorous, not quite as thorough as doing the hard sums. But that's not true. That's an illusion. Iteration allows us to go from some starting position, any starting position, and hit some goal, any goal. To do that, all we need to do, we don't even need to be smart enough to know how to start. All we need is that we need to identify a measuring stick that says, are we closer to or further from the goal? And then we can start iterating. We could even, it's not a good idea, it's not the best idea, but we could even start iterating in random directions and saying, does that work? And we say, no, that takes us further away. Okay, well, we'll discard that step then. And then we could say, does this work? And you say, yes, that moves us closer. We'll keep that one then. And then we keep doing that until we hit the goal. This works even if we move the goal. As long as we also, when we move the goal, we change the measuring stick, so that determines that we're closer to the new goal instead of the old goal, we'll still hit the goal. This is profoundly powerful. Iteration is not an informal, less rigid way of doing things. This is the way that you solve really hard problems. This is how science works. This is how good engineering works. The next part of this is feedback. In order to iterate sensibly, we also need to be able to learn from that iteration. So we need feedback. In my little diagram, the feedback is the measure on our measuring stick that we're using. That's one way of gathering feedback. And so we can learn from that and determine whether we're getting closer to our goals or not. Another way of thinking of feedback is this. If we were tasked with balancing a broom, there are two ways that we could probably think of going about that. We could do the waterfall approach to balancing a broom. We could say, I remember from high school physics that in order to be able to balance something, I've got to determine the center of mass and then organize the center of mass so that the point of contact with the surface that I'm balancing on passes through the center of mass in a line and all of that kind of stuff. And then with great skill and precision, so we're going to have to do this, we're going to have to move the broom. With great skill and precision now, we've got to position the broom so that there's no impulse left that's slightly accelerating the broom one way or another. And essentially, there's one solution to this problem. That's the real trouble with waterfall development. There's essentially one solution, the one that we planned at the start, because there's not enough feedback, there's not enough learning going on to be able to change our minds. This is a stupid way of balancing a broom. It's a stupid way of organizing software or doing anything complicated either. What we'd really do, if we were tasked with balancing a broom, is not this. What we do is we do this. We get the broom, we put it on our hand, and we'd start wobbling our hand about, and we'd sense which way the broom was tilting, and we'd move our hands to correct it. That's feedback. And this is how we'd really do it. And that's powerful enough that it not only works for brooms, that's the way that rockets fly. That's the way that rockets steer. Rockets have sensors in the rockets to figure out how much they're tilting, and they have vectored thrust for their engines so that they can steer the engines, and they can balance the broom in exactly the same way that we balance the broom on our hands. They balance the rocket on the thrust of the engines to keep them going in the direction that they want them to. This is the much stronger, much more powerful way in which we can cope with change. So by optimizing for fast iteration and clear, high-quality feedback, we have a dramatically higher quality process, and a better chance of coping with change, a better chance of learning. Next in my list is the idea of being incremental. Incremental is really sort of building up, sort of guided evolution. We don't really build software, we grow software over time, step by small step, and we kind of guide the growth of our software. It's kind of steered evolution of complex systems anyway. This is an example from the real world. This is the first module of the International Space Station. This was a Russian piece. This was launched early on in the program of building the International Space Station. And although they had ideas about where this might go, this wasn't a hard and fast plan. We often think of big engineering like the space programs as being big engineering and really planned in great detail. That's not really true. They were very iterative. You have milestones. We need to get to this stage before we can move on to the next stage. But then there's lots of iteration and lots of exploration and lots of feedback and incremental design and development that goes on in between. In this case, we started assembling more and more pieces, and eventually we get with what's widely talked about as the most complicated machine in the world. Usually, if somebody's asked the question, what's the most complex machine in the world, they point to the International Space Station or the Large Hadron Collider. I'd argue that both of these pale into complete insignificance compared to the internet. So the stuff that we build, even small systems, are hugely complicated compared to most physical things. And so we need to think about that and take that into consideration too. Next in my list of 5 things is to work experimentally. If we're going to be iterative and gathering feedback and trying to steer the direction, we need to be able to try stuff out. Now, when I talk to people about being experimental, I sometimes get the pushback and say, oh, being experimental is too scary. We can't afford to fail. Well, if you can't afford to fail, you can't afford to do anything, because you can only repeat what you've already done, because that's the only way to be safe, or ideally don't do anything at all. And that's just certainly not software development, because it stopped by then. So we must be able to experiment. And being experimental doesn't mean being reckless. It means trying out ideas in controlled circumstances and doing things like controlling the variables and understanding the information that we gather back from our experiments and learning from those things and adapting based on what we learn. Otherwise, how else is it even possible to think about making progress? These sorts of techniques are really what fundamentally define, I would say, the scientific mindset, the engineering mindset, and the agile mindset. Inspect and adapt is at the core of what we would think of as good software development. Let's take that just a little bit step further and move that into a little bit more rigorous and really think of what we do as experiments, and we get an even bigger gain. Another example from history, and in this case, again, the aviation industry. You might be able to tell I'm a space and aviation nut, but for years, the way in which you introduce a new aircraft is not by just projecting, ta-da, here's a new aircraft, because that kills people. What you do is that you say, well, I'd like to introduce a new aircraft, but I'm not quite sure whether it's all safe. So there's a rule in test aviation that you don't introduce a new power plant and a new airframe at the same time. So what you do is you have an old aeroplane and you bolt a new engine onto the front. And you try that out. Some brave test pilot goes and flies the thing and sees whether they can survive the experience or not. And if that works out okay, they say, good, that's good. Okay, so now let's get a new airframe and we'll bolt an old engine onto it because the engine's nice and reliable, and then we can try out the airframe. And another brave test pilot goes and flies this and see if they can survive that. And if that's all okay, they say, good. And now we can put the two new bits together. We can add the new engine to the new airframe and then test fly that as well. And aviation's made that they learned that lesson, I don't know, probably sometime around the First World War, sort of 1914, 18 kind of period of time. That's when they started doing that. And then after that, in the 20s, they started doing that kind of always. They still do that today. And the last one, one of the things that I think differentiates engineering probably from pure science or maths is being empirical. And pure science and maths certainly take this on board, but I think this is really fundamental and foundational to engineering thinking. Being empirical is learning from the real world. This is a nice example of empiricism. We've just talked about aeroplanes and engines and power plants. This was the first production jet aeroplane. This was a German aeroplane, a Heinkel, that was built during the Second World War. And this was the first production. There were other things that had done as prototypes, but this was the first production jet aeroplane. And they got this kind of wrong. So they did what we talked about. They bolted on a propeller engine onto the front of this and flew the airframe with the propeller engine first. And then they got to this stage, that they were trying the jet, and they put the jet engine onto an old aeroplane. They flew that first. Then they did this. They built this, and you can see that this is tilted. So this is what aviation people call a tail dragger, because it's dragging its tail along at the back. There's a little wheel at the back and there are two big wheels at the front. The reason that aircraft designers did it like that was to lift the nose up so that there was room for a big propeller at the front, so that it could be nice, have a nice powerful engine. But now we've got a jet engine. So they did this, they test flew this, and it melted the runway because the engine's pointing at the runway. They hadn't thought of that. If you look at nearly all jet aeroplanes these days, they sit flat like that. So they've moved the little wheel to the front. They've moved the big wheels a little bit further back behind the centre of gravity, so it stands on the wheels. And that's why they're organised like that. That's the kind of empirical learning from practical experience. Oh, we didn't think of that. Let's fix it. Here's another example of being empirical. This is the Elon Musk's and SpaceX's Starship. If this will be a revolutionary device, if it happens, this will be a reusable space rocket, and it's going to lower the cost of getting stuff into space dramatically, orders of magnitude, if it happens. And this is a picture of one of them blowing up. Nearly all of them have blown up to some degree so far. But they're making huge progress. This isn't a failure, this is a success, because it met all of its mission parameters. This was just the pushing a little bit further and seeing whether you could also do this last bit of landing it. But they learnt a lot by trying things out. So experimenting, trying things out in safe conditions. There are no people on this. There are no people nearby. They're trying this in under controlled circumstances, as far as you can blow up rockets in under controlled circumstances. That's what they're doing. The other aspect of all of this is just how complex modern software is. The picture in the middle with the Amazon label is not a diagram of individual classes or anything like that. Those are microservices. And actually, this is a still from a movie that's dynamic and evolving all of the time, because that's how a large microservice environment looks in the wild. These are complex things. Nobody's really going to understand this, even the people that are in the depths of that working on those microservices, because they don't know what other microservices are live at the same time as theirs. That's the nature of this game. This is genuinely world-class complex stuff. And so we need to start thinking about that and start thinking about ways in which we can learn from that and control it. So as well as being about learning, software development is fundamentally about being able to manage complexity too. Managing complexity. I have another 5 things: modularity, cohesion, separation of concerns, abstraction, coupling. Once again, I know that everybody in this room is going, yeah, Dave, we know about those things. But what I'm saying once again is not just, aren't these good ideas? I'm saying, whenever you have a choice in software development or design or team organization or anything, whenever you have a choice, prefer the choice that improves the modularity, the cohesion, the separation of concerns, the abstraction, and the coupling. If you were to follow that advice, I would suggest you've just ruled out a whole bunch of stupid ideas and given yourself an opportunity to pick some of the better ideas. And I think that's what we're looking for from an engineering discipline. So once again, let's look at these in a bit more detail. Starting with modularity. I keep talking about aeroplanes. Here's another picture of an aeroplane. The aeroplanes are very modular systems. One of the advantages of a modular system is that we can do maintenance on one part of the system without having to worry about the rest. We can also change out the parts. We could replace this engine with a more efficient engine, perhaps, or something like that. And also, we'd hope that if we make a change to the engine, we're not going to break the flight entertainment system or the controls that steer the aeroplane. These are modular systems. They are discrete, and we're engineering each of those things to be robust and useful in its own right. something a bit closer to home. This is an exploded picture of an iPhone. And even something as densely integrated as an iPhone is still a modular system. There are still parts of this, components of this, that are discrete and focused on different parts of the job. This seems obvious, but I'm calling out there's a lot of software that doesn't look like that. A bit closer to home. As you can tell by looking at me, I am very old, and I've been writing software for a long time. And when I started writing software in the 1980s, if you wanted to print something out, you had to know exactly the printer that you were talking to. And you had to write the codes that drove that printer, and programming an Epson RX80 was different to programming an Epson FX80. The codes were different. It was just a nightmare. And then later, what happened was the operating system vendors thought, this is stupid, so let's raise the level of abstraction a bit, and we'll create a modular system where we can plug in behind that abstraction different modules of code that know how to talk to different types of printers. So now we can just say, our code can just say print, and the printer driver does the hard work of translating to the detail of how the printer works. That's one of the other benefits of a modular system. Here's some code. Here's some code that's not very modular. This is written in C, but just because you're writing code in C doesn't mean you have to write crap code. And in this code, there's this if statement. And this is 361 lines in a single if statement. My usual feedback that I get when I show people this code is, oh yeah, Dave, we've got if statements with much more lines than that. That's not a good thing. This is what this looks like. If we try and visualize this is what this looks like. In reality, there's a huge part of this function that's just this if block. So I had a little look at this to try and figure out what it's doing, and it's not very nice code, and I didn't enjoy myself very much. But I think that all this is doing inside this if statement is this. If there's no connection, create a connection. So if I just do this, if I just name what's going on inside the if statement and name what's going on in the if condition and pull all of this crap out of here, I've just made the code more modular. Just that step has improved the quality of this code. I looked kind of where, in the context of where this code came from, and I thought that were probably 3 or 4 other versions of this. This fixes that problem in one step. By making this code more modular, I've now an opportunity to use it in multiple places. So this is stupid code doing it this way, and just by preferring it to be modular, we can improve it. And doing no more than that, just following that line of reasoning. Always, I would say. My favorite description of what high-quality software is about comes from our keynote speaker for tonight, Kent Beck. And I've always loved this statement of Kent's, which is good design is about moving the things that are related closer together and the things that are unrelated further apart. It's classic Kent Beck in that it's kind of slightly amusing and slightly humorous, but it's also deeply true. And I think that's really what we're talking about. Modularity is fundamentally about moving the stuff that's unrelated further apart, and cohesion is about moving the stuff that's related closer together. And if we do both of those things, we got better code. I think there's not much argument that that's true. One of the techniques that I've found visible, I had the pleasure of working with a friend of mine who I value very highly as a software developer, and one of the lessons that I learned from him was he has a laser beam focus on separation of concerns. That is, we want each part of our software to be focused on doing one job. At whatever level of granularity we're talking about, we want each part to be focused on doing one thing. And as soon as he would see that it was the piece of code he was working on was doing 2 things, he'd be there tearing it apart to try and figure out he could change the design to separate the concerns. I've learnt that from him, and now I'm maybe not quite, but nearly as robust in my application of separation as concerns as he is. Here's another example from the real world. This is an electric BMW. And BMW fairly recently made the choice to separate the concerns of the physical transport of a car from the utility of the vehicle. They've done this by creating a platform for their electric cars. So all of the batteries, the motors, the steering mechanisms, and so on, the charging mechanisms and all of that sort of stuff is just generic. And then you have a shell. You have, if you want a sports car, you kind of put one thing on. If you want a sports utility vehicle, you put another one on. If you want a family saloon, you put another one on. And this gives them a lot of flexibility, gives them a lot of options. It means that they can upgrade either part separately from the other. They can innovate and come up with new parts. This is a more modular system as a result of striving for this separation of concerns. These are good design principles, even if we're talking about cars. Next is abstraction. Here's another car. This is my favorite car in this presentation. This is clearly a very ancient car, and I think it's a beautiful picture. But this is not a very abstract system. You can see what's going on here. And here, this lever is, I think if I'm interpreting this right, this is both the throttle and the brake in a single control. They haven't yet decided that these would be better if we separated the concerns here. But that's the way that this works. And then this thing that looks like a tiller is a tiller. It's a steering mechanism. And you can actually see, if you look carefully, you can see the links. You can see that that little handle's connected to a tube that goes down here, and there's a little lever here, and that's connected via a little push rod to the steering mechanism on the front of the car. So this is not a very abstract design. What happened when we start thinking about steering in cars is we started abstracting things. This is still a very old car, and you can see that there are some differences to a modern car, but we're starting to see things that look a bit more familiar in terms of the controls of a car. And then this evolved over time until we get to something that looks more like a modern steering wheel in a modern car. So I want to ask you a question now, is how does the steering work? You don't know. Even if you think you know, you don't know, because it might work a whole variety of different ways. It might be that this steering wheel is connected through parallelogram steering or rack and pinion steering as a mechanical connection to the wheels. It's similar to the old car. Or it might be that this is power-assisted steering, and that this is driving through hydraulics, things that push rods that move the wheels. Or probably more likely these days, it's electronic. This is actually like a joystick control on your computer. It's sending digital signals to some kind of computer that's then interpreting and driving electrical actuators, motors of some kind, that are actually moving the wheels around. We don't know, and we don't care. That's the important thing. Not caring is the important thing. We can drive this car, we can steer the wheels without caring about how that works. And that's a really, really good thing. It means we can jump from car to car to car, whichever version of the steering mechanism is in place, and still drive the car. We can use it. That's a good thing. That's a good design property to have. Let's look at this in the terms of code. So we're going to, we've got some code, two pieces of code talking to each other. It's going to initialize and get the delivery date and get some VAT, and then comes some total for order. And just for fun, I've put a lovely little back channel to the database, so we're sharing data through a database. I'm hoping everybody's shuddering slightly at this point. This is hideous. We don't want to do this. And so what we could do instead is we could kind of change the level of abstraction. We could try to be clearer about what it is that we're really doing here. So we could do something like this. We could say, instead of that, let's say we're going to place an order, and then we're going to say the order's placed. That's nicer, isn't it? That's better. My bet is you'd prefer to work on a system that had conversations like this rather than conversations like the first one. Abstraction should allow us to keep secrets in different parts of the code. We should be able to make changes in one part of the code and not care what's going on in another one. And this is closely related to one of our principal enemies in software, which is coupling. Here are 2 versions of Lego systems. I warned you that there would be Lego. When I was a little boy, this was what Lego was like. It was a bunch of bricks. And you could do what you like with a bunch of bricks. I'm now a very proud grandparent, and I have 3 lovely grandchildren. And when I'm playing Lego with my lovely little granddaughters, and they build some kind of weird shape, I say, "Oh, that's lovely, darling. What's that?" And they'll say, "Oh, it's a giraffe." And I say, "Of course it's a giraffe. It's a wonderful giraffe." And you go, "Doesn't look like a giraffe." But our imaginations fill in the details, and they're so flexible. And they could build a spaceship or a car or a giraffe or anything that they like. This is a very, 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 very different kind of system. There are probably not an infinite number of ways, but there's a very, very, very large number of ways in which we can assemble Lego bricks like this. There's one way in which we can assemble this and end up with this car. I can't even build a Maserati, let alone a spaceship or a giraffe from this kit, because the pieces are wrong. Now, there's a place for both of these things. Both of these things are appropriate in their context. So I'm not saying we should always go for loose coupling. Sometimes tighter coupling's a good thing, but we've got to understand the context and make the choice. My advice is to always manage coupling, and that should be one of the things in the forethought of your mind, because coupling is one of the most difficult problems that we deal with. And by managed coupling, my advice is to get a coupling at the appropriate level with a preference towards looser coupling rather than tighter coupling. If you've got 2 choices, always pick the looser coupling one at any particular point. You can take that too far, but that's my advice. Let's look at some code again, or rather some pseudo-code. So here's my 2 pieces of software again, and this time I've decided that I'm going to change the date format in the orange one. So if we had the old kind of conversation that was like this, at the point at which we're returning a date, we've broken that. And because this is coupled and all with that, we're probably going to break the database as well, and we've just blown up our system. If we've done the nicer thing, if we've abstracted the conversation, we've also reduced the coupling between the conversation. So now we have more options. So, for example, we could choose, and it's quite a good choice, to put a little translation point, a port and an adapter kind of thing between this piece and this piece. So now when I say place order, this could recognize that that's an old version 1 place order. Say, you're giving me old-fashioned dates. I'm going to translate that into my shiny new dates. And when I send you a message back, I'm going to translate that into your boring old-fashioned dates. And now our software stays working. So by thinking in these terms and using those sorts of techniques, it allows us to move forwards. We are behind time. I'm going to run through this very, very quickly. So I want to talk about these ideas of managing the collection. This is more than just apple pie. These are tools. I want to try and surface this with some code. So here's some code. And this is a car, and I've got a petrol engine and a method called start, where I'm going to put the brakes into the gears into neutral. I'm going to apply the brakes, and then I'm going to start the engine. And so let's write a test for that. So should start car engine. I'm going to create a car. I'm going to say start, and now I can't assert anything. Damn. There's nothing I can assert, because without breaking the encapsulation of that thing and seeing what's actually going on in the private engine, I can't really see what's going on. So this is not really testable code. So now what I'm going to do is I'm just going to make my code more testable. And I want to see what the impact on all of those properties of good design are if I just do that. So let's start with a test. And I often write tests backwards when I'm not quite sure what I'm going to do. I find that easier. So what I'd really like to be able to do is I'd like to assert that the engine started successfully. And that's going to happen when I call start on the car. And for that, I'm going to need a car and a car with an engine. But now I'm going to pass in the engine because I need to be able to do this at the end. I must do that. And so now I'm going to fake an engine. And that was kind of driven by this decision that I wanted to be able to make this testable. I'm adding a measurement point into the design of my software, if you like, that allows me to better say, yes, I'm just talking about dependency injection here. But I want to see the impact of this on what this means to my design. This is my fake engine. It just records the fact that the engine was started. That's all it does. I'd probably mock that in real life, but I just wanted to make it clear in the code. So now here's my better car, and here's my test. And this is a better car, not just because I'm saying so, because this applies those properties. It's different from the original car in the sense of the dependency injection, which means that my better car is more modular. It knows less about petrol engines than it used to. It's only by a little bit, but that's a better choice. It's more cohesive. All of this code is about carness, and it's nothing to do with engineness. It doesn't need to know, once again, how to create a petrol engine, which is about being an engine. That's nothing to do with cars. This is a better separation of concerns. All of this stuff is about cars. All of the other stuff about engines is somewhere else. This is more abstract. I'm now talking to an engine abstraction rather than a particular kind of engine. And it's reduced the coupling, because now I'm not tied to how to create that bloody petrol engine. This is better code. Only by preferring to make my code testable, and only by keeping those ideas in the back of my mind. Testability amplifies our ability to add the properties that we value in high-quality code. The outcome of this is that I can still create exactly the same car that I had before. Precisely the same. Get the same behavior, works just the same. But I can also now, at runtime, if I choose, create a better car with an electric engine and help save the planet. Or if I'm some kind of nutcase, I can create a better car with a jet engine. My code is more flexible, has greater utility, more use cases, easier to understand. It's just better code. I'd like you to just try a brief thought experiment for a moment. Let's do 2 experiments. So let's imagine that we're working on a project, and we're going to not optimize for learning and compare that with optimizing for learning. So let's imagine our project. We're going to start off and we're going to think really, really hard, and we're going to completely understand the problem. We're going to completely understand the solution, and then we're going to start. We're not going to try anything out. We're not going to test anything, because that's learning, that's iterating and feedback. We're not going to do any of that stuff. We're going to make progress, and we're just going to go forwards, and we're going to get to the end, and we'll win. That's like trying to balance the broom by just positioning it and doing the maths. The chances of success are minuscule if that's the way that we operate. That's essentially what a waterfall project is doing. It's trying to predict all of those things at the outset. There are very few feedback loops designated in the usual version of waterfall. The man that invented waterfall said we should do feedback, but he was misunderstood for 50 years, so it's a shame. Now let's think about the other ones. Optimizing complexity. Imagine some piece of code that you're familiar with. Imagine 2 versions of it. One is modular, cohesive, good separation of concerns, nice lines of abstraction so you can talk to one part of the code without worrying about how it works. Loose coupling so that it's flexible and it's testable, all of these nice things. And now imagine another version of that code. There's no modularity, so it's in one big file. There's no cohesion, so the behaviors are kind of spread through all in different places throughout that file. There's no real separation of concerns. This one big file is doing all of the things. It's talking to databases, it's showing things on the screen, it's doing calculations, it's talking to other bits of software. There's no lines of abstraction going on. The whole thing is coupled. I don't think you have to work very hard to imagine that second version of the software. This is so common that we even have a name for it. That's what we call a big ball of mud. They're incredibly common. They're probably the commonest form of big software. But that's what they look like. Now, which one would you prefer to work on? I guarantee it's the first one. It's going to be a much nicer experience. Now, think, in all of my conversation, apart from the code examples, in all of my conversation this morning, I haven't once really mentioned the technology, the frameworks, the problems that we're solving. These ideas are wholly generic. It doesn't matter whether you're doing no-code software or assembler. It doesn't matter whether you're doing functional programming or object-oriented programming, building space shuttles or building your mum's website for a cake shop. It doesn't matter. All of these things are still true. I think that's what engineering would look like if we could come up with engineering for software. To the organisers who are now getting worried, I am very close to the end. These things matter for one reason, and really one reason only. They allow us to change our software. All of them are really focused on maintaining our ability to change our software. Change is entirely pervasive. Whether we initiate the change or whether the world initiates the change. We can build the most secure system right now and then somebody finds an exploit in the operating system that we're running on and just blown all of our assumptions out of the water. We can build the perfect system for our users right now and then we find out that actually the users have moved on and they now want something else. Change just happens all of the time. There's no avoiding it. And so what we must do is that we must sustain our ability to change. I would argue that we should adopt the idea as core to our discipline that the quality of the system is defined by our ability to change it and nothing else. Now, of course, that's not enough. Of course, we need secure systems, resilient systems, performance systems, whatever else it is. Those are all important things, but we can never get those things unless we can change the software. The alternative is we have to get all of those things perfectly right first time. So working in a way to sustain and maintain our ability to change our software is fundamentally what defines the quality of it. If your software is hard to change, it's not high quality, is the idea that I would like to leave you with. I hope you have a wonderful time at the conference. Thank you very much for listening to me. I'll be around for the rest of the day for questions. Thank you.